Hi, I'm Devendra Kapadia. I'm manager of calculus and algebra at Wolfram. And this morning at 11 o'clock, I'll do a talk with Adam Strzebonski, a senior developer on Asymptotic Solvers. I hope to see you there. Thank you.
So it's another joint talk with Devendra, and we will be talking about asymptotic solvers. So here's the plan for the talk. First, I will talk about asymptotic solve, and then Devendra will talk about asymptotic R-solve value and asymptotic sum. So these are new functions in version 12. So first, asymptotic solve. So again, suppose we want to solve the equation in two variables for y as a function of x. So we can get global algebraic solutions with solve, and we can get a solution over the reals. And using asymptotic solve, we can get local solutions near a specified value of x. So this gives us all complex solutions as Poisson series in this case. And we can also ask for solutions that are real. We have to specify that they are real for positive x near 0. For negative x, we would have to use direction option. So we have three solutions, and we can check that the asymptotic solutions will approximate algebraic solutions near 0 for positive values. So here is one of the roots become complex. But here, near 0, there are three roots, and they're well approximated. So let me talk about what are the solvable cases, or what cases can we solve at that time. So first, the nicest case, the regular case, the case of non-singular points of systems of analytic equations. So we'll use analytic implicit function theorem. This theorem is true for x and y of arbitrary dimension. So if the derivative is inverse with respect to y is invertible, then locally we have exactly one solution, and this solution is analytic. So here's an example with n and m dimension 1. So here's a function. Let's check function is 0 at 0. Its derivative is not 0. So we should expect one analytic solution. And indeed, we get a power series with integer powers. And we can check that the solution is a good approximation for the function. It's pretty difficult to tell them apart. So let's try an example with now n three-dimensional and m two. So variable x is three-dimensional, variable y is two-dimensional. So we have two equations. We check that the equations are 0 at 0, and that the determinant of the derivative is not 0. So again, we can expect analytic solution. And here is the solution. It's a power series now in three variables. And let's do this trick with substitution of new variable times each of the variable to since we don't have right now multivariate series in Mathematica, that's what we do to simulate multivariate series, and we can see that substituting the solution into the original equations gives us something which is of order t to the third power. We asked for the third order solution here. So it indeed satisfies the equations. We cannot plot it. It would be five-dimensional. So the next case that's solvable singular points of analytic equations. Now you can notice that this works only if x and y are one-dimensional. So that's a much narrower case. So if we have an analytic mapping from C2 to C, the function is 0 at AB, and the first k minus 1 derivatives are 0, and the kth derivative is not 0, then locally the solution is, there are k solutions, and the solutions can be represented as Poisson series. So series with fractional exponents. So here is a function. We are solving for y in terms of x. Let's see that at 0, the function and its first 3 derivatives are 0. The fourth derivative is not 0. So we can expect 4 solutions that are Poisson series. And asymptotic solve should shortly give us the solutions. Here they are. And indeed, they have fractional powers. We can also ask for real solutions for positive value of x. So here is we have just 2 real solutions, and we can check again that they approximate the exact solutions pretty well. So what's the next solvable case? Singular points of algebraic curves. So now we can make y multidimensional, but at the cost of assuming that all the equations are polynomial. And in this case, we also get Poisson series solutions. So here's an example with x and y one-dimensional. Here are the real solutions, and here are the real solutions with direction from below. So depending on which direction we are approaching from, we'll get different number of solutions and different solution, different series. And let's see. So the exact curve is the blue curve, the trifolium, and we got the approximations of the solutions near 0, near the singular point. Okay, let me show the example with n equal 4. So we have 3 equations in 4 variables, so we can get solutions for 3 variables as Poisson series in the remaining 1 variable. And we can substitute back into the equation, take series to check that we got the correct result. Okay, so the next solvable, or the next slightly different problem that we are solving, we are looking for asymptotic solution near a given value of the independent variables. So what we are checking before, we are specifying both the value of x and the value of y. Now we are just specifying the value of x and looking for all the values of y for which there is a solution. And this requires the equations to be polynomial in the dependent variable so that we can guarantee that there are finitely many solutions. So it has to be polynomial in y, can still be analytic in x, and we get Poisson series solution. We check that it satisfies the equation. And here we try a system of 3 polynomial equations. Again, one independent variables, but 3 dependent variables. And we get several solutions that are Poisson series, and we can back substitute to check that we get zeros up to the specified order. Okay, so the last solvable case. So now we are, all those situations we are looking at regular points of the equations. Now we are looking at singular point of equations. So suppose we want to solve an equation for this equation, right? So it's an exp-log equation. So it's exp-log in terms of x, the variable x, the independent variable, and polynomial in terms of y. And we want to solve it near infinity. So infinity will be a singular point of this equation. It's not analytic near x going to infinity. And what we can hope for in this case is solutions that are exp-log functions in x, and are, so they are actually real exp-log functions plus real exp-log functions times I. So let's see what the solutions will look like. Right, so basically if we expand it, we can see that there is a real part and an imaginary part, and each of them is a real exp-log function. And this just gives us the real solution. So just one, the last one is real. And we can check that indeed near infinity we get a good approximation. So the blue line is our asymptotic solution. The yellow line is the exact solution, and we can see that near zero it's a different solution, then it jumps, and then it's pretty much equal to our asymptotic solution. We cannot even see the difference because everything is exponential here, so the difference disappears pretty fast. So that's all I have. Now Devendra will continue with discrete asymptotics. Thank you.
Hello. Okay, so I'll talk now about asymptotics and discrete asymptotics. So in version 11.3, we had this idea of continuous asymptotics. So we had functions for differential equations and integrals, and now in version 12, we have functions for differential equations and sums. And although the discrete case came second, there's a good reason. So first of all, continuous asymptotics works in things like physics, fluid dynamics, and let's say special functions. But if you go to discrete asymptotics, you are into computer science, number theory, combinatorics. So the whole world has changed. When you do continuous asymptotics, you could be at 0, 1, infinity, wherever you like. If you do discrete asymptotics, you're always at infinity because it makes no sense to talk about a sequence at 30. Just put the value in and you get the answer. So one last point, that although the two are different, the discrete case relies on the continuous case for many kinds of classifications. So if you know continuous asymptotics, you pretty much know the discrete case as well. So some simple examples of discrete asymptotics. So let me begin now with asymptotic R-solve value. So here's a difference equation. You can see that the 1 is much larger than the 1 over n cubed. So when you solve it, you get back basically a kind of Taylor series at infinity. You plug in a value for the constant C1, plot it, and just for comparison, look at how beautiful the asymptotic series is, and simple, and how difficult the exact solution looks. So that's a dramatic simplification. So that's a Taylor case, and then on to kind of the Frobenius case from differential equations, from a course on differential equations. So here what happens is you get a Frobenius solutions, the differential equation is going, the difference is going a little slower, so faster. So then you get a Frobenius solution. Here's a plot, it goes much faster now. So in this case, you have a square root of n, which is the sign that you got a Frobenius solution. It's going to blow up, and that's the square root of n term. Okay, so from Frobenius on to the irregular singular case, And this difference equation, I'm sure you all know, it's just a difference equation for gamma. So what do you expect? You expect the Stirling formula, and lo and behold, there's what you get back. So you have ordinary point, regular single point, irregular single point, just like differential equations. Here you plot it, and you find that it's really quite hard to plot because you have a very, very fast growth rate. Okay, there. Okay, so let me plot it over here, and the curve just shoots up rapidly because it's moving very, very fast. Okay, now question is, why don't I have initial values over here? Well, the story of this goes back to Birkhoff and Poincaré and people like that. So here's a sequence of involutions from combinatorics, and I can use find sequence function to work out the difference equation for it, but then I'm stuck. And the reason why I'm stuck is because basically what's happening is that you have initial values at one end, you want to approximate the other end, there's no way to do it. And so Paul asked me this question, the answer is you have to use an approximation over here. I'm sure Birkhoff knew it, I'm sure Doron-Zeilberger knew it, and all you can do over here is to compute an approximate solution to this problem. You can see you've got a decimal point over there, which is going to let you do things. That's quite a hard computation. It's got to go into limit, work out leading term, and then work out the asymptotic. But it's done that. That's from a paper by Doron-Zeilberger from the 1980s. He spends 10 pages. We can do now at half a line now. So that's the approximate value for 1,000, and here's the exact value, and you see all is fine over here. Okay, so before I leave the topic, something about perturbation problems where you've got a parameter epsilon, and what happens over here is you have a solution which has a parameter in it, in the answer, and the exact solution is a geometric sequence, but the approximations have got some kind of peaks in them. Okay? So on to the next theme, which is asymptotic sum. Now, for version 7, we actually did a really nice job of summation, and I thought there's nothing more to do over here. So at that point, we had done every single algorithm we knew about, and I was not too keen on doing this function at all, but I've learned a lot. So here's the first example where you have a kind of rational sum, 1 over k squared plus 1, and ask for an asymptotic, and I get back a series at infinity. Now in this case, of course, there's an exact formula from sum itself, and if you do a series expansion of that, then you get back just the same result. Not very interesting, but the polygamma function in discrete calculus plays the same role as the logarithmic function in continuous calculus. So if you integrate a rational function, you get logarithms. If you sum it, you get a polygamma. Okay, slightly harder question. Here is the Q rational sum, 1 over 2 raised to k plus 1. And now we use the Euler-Maclaurin formula, which actually computes the integral as an approximation for the sum. The problem is that even Euler knew it, that there's one Euler gamma for every sum. And the Euler gamma for this sum is Q polygamma. So when you do asymptotics of sums, you need to invent one Euler gamma for every situation. And that's the one for this one. Okay, now let's try the numerical values. And you see they give quite a nice approximation. So here's the exact answer, and you get a pretty nice approximation. And as the last example, I want to take up an infinite sum. Now, this example we cannot do in sum. I searched hard. It took me some months to find, but I found it. Okay, so this example works using a technique due to Philippe Flageolet, and does a Mellin transform computation with the parameter x, goes in Mellin transform space, sums over there, does a residual computation, comes back. All that in one line. It's a beautiful paper by Flageolet, and it takes a bit of time because it's a hard computation. But we have Mellin transforms, we've got residues, we've got everything, and it will come back with the answer in just a minute, okay? But the main point is this is a really, really good approximation, as I'll show you in just a minute, okay? So, yes. Okay, so there I am. Okay. So here's the approximate value, here's the numerical value, and they look quite nice and simple. Okay, so I'm done, and the main point is that for version 12, we have discrete asymptotics and algebraic asymptotics. And now in version 12.1, we want to put it all together and have one massive asymptotic function which will do everything for you. Just put your difference equation differentially what you like, it'll go and do it for you. And then we are done. Okay, thank you very much.